Good morning, students. This is Shravanti dealing the subject digital signal processing. Up to now, we have completed almost 3 units. Now I concentrate on the 4th unit, that is the digital filter designing. It is very important unit. Here, the contents are causality and its implications, practical frequency selective filters, designing of the digital filters like FIR filters and IIR filters using different techniques. Now we start with the introduction, that is what is the filter and general examples, and the terms LTI systems and filters are synonyms. Why and what is the importance of the filtering in digital signal processing, and also ideal filter characteristics. Now filter. So filter is nothing but it is a device which attenuates unwanted components and passes only the desired components. So you can say this in different manner like this. It is commonly used to describe a device that discriminates according to some attribute of the objects applied at its input what passes through it. So the general examples here, we may take coffee or juice filters, air filters, oil filters, UV filters in photography. Suppose if you consider one juice filter, that filter passes only the desired juice, not the undesired pulp. Coming to the air filter, that air filter filters the air from the dust particles that are presented in the air. Oil filter also here, that filter separates the oil from the dirty particles. Coming to the UV filter, which is widely used in photography, that filter attenuates the ultraviolet light and allows only the visible light which is necessary for the photography. So in the same way here, we will focus on the LTI system. Here we know that the system just modifies the input. That modified one appear as a output. That is the response of the system. Of course, we know this one. So here, in the same way as a filter, the LTI system also performs a type of discrimination or filtering among the various frequency components at its input. The nature of this filtering action is determined by the frequency response characteristics, that is H of omega. Of course, we know that H of omega depends on the coefficients AK and BK. That means A0, A1, A2 and so on, B0, B1, B2 and so on, which is discussed in the 3rd unit, digital structures. That means here the system filters the desired frequency components and undesired frequency components. Here, by proper selection of the coefficients AK and BK, we can design filters that pass the signals with frequency components in some bands, while they attenuate the signals containing frequency components in other frequency bands. That's why here the filter or the LTI system is also called as frequency selective filter or spectral shaping filter. Why? Because here our LTI system, linear time invariant system, or the filter selects only the desired frequency components of the input, not the undesired frequency components of the input. In the same way, it shapes the frequency components of the particular input signal. That's why it is also called as spectral shaping filter. Of course, we know that frequency components also called as spectral components. That's why here we may call this filter as a spectral shaping filter, which modifies the input spectral components. Here, coming to this one, the well-known equation, what is that? Y of omega is equal to h of omega into x of omega. Here, x of omega is the frequency spectrum of the input signal. H of omega is the frequency spectrum of the system. Y of omega is the frequency spectrum of the output signal of the particular system. That means the system output depends on the input spectrum and also the system spectrum. So, here the input spectrum that is modified based on this h of omega value, and then you can get the new spectrum like y of omega. That's why here this h of omega is also called as weighing function or spectral shaping function. So here from all this we can conclude that both LTI system and filters are used interchangeably, and we can say LTI system is nothing but filter. Coming to the next one, what is the use of this filtering action in the digital signal processing? So here these are the different uses. The first one is removal of undesirable noise from desired signals. And the next one is to shape the spectral components, which is widely used in communication channels. And the next one is to detect the signals like in radar, sonars and communications, and also to performing spectral analysis of the signals. That means here altogether we can say by using this filtering action, our LTI system removes certain unnecessary noise and also shapes the input spectrum and also detects the signals, different signals, whatever we want, and then we can analyze the output spectrum. So here these are the few uses. And coming to the filter characteristics, actually here we are taking initially ideal filters. Ideal filters, of course, we very well known about this topic. That means we have the different filters based on the frequency domain characteristics. Those are low pass filter, high pass filter, band pass filter, band stop filter, and it is also called as band elimination filter. And of course we have the another filter, that is the all pass filter also. Here I concentrate on the first one. What is that? Low pass filter. This is the magnitude response of the filter. Of course you know that the frequency response, the symbol is h of omega, and the graph h of omega versus omega is called as frequency response curve. Here it consists of two curves. One is the magnitude response, and the other one is the phase response. Here it shows the magnitude response, mod of h of omega versus omega. So here if you observe the characteristic or the response, magnitude response of this low pass filter, here this is said to be this is said to be pass band and this is said to be stop band. So here the low pass filter definition is it allows the lower frequencies and attenuates the all other higher frequencies. So allowing the particular frequencies is called as pass band. Attenuating the particular range of frequencies is called as stop band. So here from this we can conclude that this is the magnitude response. It passes the only lower frequencies and attenuates the all other higher frequencies. Then coming to the next one, high pass filter. High pass filter, if you observe, the pass band is here, the stop band is here. That means it allows the higher frequencies and attenuates the lower frequencies, just inverse operation of the low pass filter. Now coming to the band pass filter, here it allows the certain band of frequencies and attenuates all other frequencies. And coming to the band stop filter, that is the reverse operation of the band pass, it does not allow the certain band of frequencies and allows the other band of frequencies. So these are the different filters which are widely used in applications. So here we have to design these type of filters in the digital manner. That's why here we should focus on the designing digital filters. Coming to the characteristics of this ideal filters, if you observe, almost all the ideal filters are having the constant gain in the pass band, and here that of course here we are considering that constant gain value as unity. That means unity gain, and then the stop band has the value 0. Here coming to the characteristics, ideal filters have a constant gain, usually taken as unity gain pass band characteristic, and 0 gain in the stop band. This is the main characteristic. And another one is related to the phase response, that is ideal filters have a linear phase characteristics within their pass band. And also ideal filters also have constant magnitude characteristic. So these 2 points are related to the topic distortionless transmission through a system. So in that we discussed about this topic. Every system should give the undistorted output based on 2 important conditions. The first one is the magnitude response should be constant and the phase response should be linear and passing through the origin. Based on that, to get the undistorted output, the ideal filters have a linear phase characteristic and it also have constant magnitude characteristic. And coming to the another important characteristic, that is the ideal filters are physically unrealizable. That means it is impossible to realize this type of systems physically. So okay, we will discuss this one in the causality topic, right? Remember these 4 characteristics of the ideal filter. Next, these are the differences between analog filter and digital filter. Of course we know this. I just give the information here, you read well, and then if you have any doubts ask me later. So shortly, so digital filters means filtering the digital sequences. When compared with this one, these used for filtering analog signals. Of course digital filters are designed with digital hardware like flip-flops, counters, shift registers, under very less sensitive and give the more accurate values, and very flexible to write the software programs. And then it is the programmable one. Of course you just read and then okay. Now coming to the next one, types of digital filter. So here according to the impulse response duration, we have two different types. One is the finite impulse response digital filter, another one is infinite impulse response digital filter. Shortly, one is the FIR filter, another one is the IIR filter. The name itself gives the meaning to you. Finite impulse response means this type of filter, this type of system is having the finite duration of the impulse response. That means h of n. H of n here, h of n, the n range is finite duration, like 0 to n minus 1, like that. And then IIR digital filter. IIR means infinite impulse response. That means here the system impulse response duration is of infinite, like n is equal to 0 to infinite. If it is a causal, you may take 0 to infinite. If it is the non-causal, that is the minus infinity to infinity. Usually we are considering the causal systems. That's why here the n range is 0 to infinity. Now, difference between FIR filter and IIR filter. Of course, this one also you just kindly go through this and read well, and if you have any doubt, ask me. And these are discussed in the third unit, and that means previous units. Okay. Now, so here coming to the next one is causality and its implications. Here, the main important one is to design the system. Here, we should remember the two conditions. What is that? Causality and stability. So, now here, if you consider the causality, what is that causality? That impulse response should be 0 for n less than 0. What is that? H of n is equal to 0 for n less than 0. That means here, if you consider one ideal filter, for example here low pass filter, this is the magnitude response and this is the impulse response of this one. By doing the inverse Fourier transform, here for the h of omega, you can get the h of n like this. That means here if you observe this h of n, this is not equal to 0 for n less than 0. So that means this is not a causal system. So that means here ideal filters, all ideal filters, if you observe ideal low pass, high pass, band reject, all ideal filters are not causality, are not obeying the particular causality condition. So that's why here these are not physically realizable. So here these are the some characteristics. That means it is non-causal and of course it is, that's why unrealizable. And then if you take the particularly absolutely summable, that means summation of h of n from n is equal to minus infinity to infinity. So it is not the absolutely summable. That means it gives a finite value, and of course, and hence we can say this one is the unstable system, unstable filter. And these are the some points related to the ideal filter characteristics. And now from all this, I'm so hurry here, there is no time. That's why if you have any doubt, ask me. Okay, in the next sessions. Okay, now here causality has very important applications in the design of frequency selective filters. So these are 3 points. You should remember these 3 points here. The first one is the frequency response h of omega cannot be 0 except at a finite set of points in the frequency. The magnitude mode of h of omega cannot be constant in any finite range of frequencies, and the transition from passband to stopband cannot be infinitely sharp. The third one is the magnitude mode of h of omega and phase theta of omega cannot be chosen arbitrarily. So ideal filters cannot agree with all this. That's why here we should go to the practical filters. Here I am saying practical frequency selective filter characteristics. So okay, here This are the particularly the practical characteristics of the low pass filter. If you observe here, there is no continuously zero stop band here. So from the here first point, so cannot be zero, h of omega cannot be zero except at a finite set of points in the frequency. That means here in the previous case, if you consider ideal low pass filter, the stop band h of omega is zero for all frequencies in that particular range. But here if you observe, the particularly for the set of frequencies only, it gives the value 0, not the for all certain band of frequencies it cannot give the 0 value. Okay, that is the first implication. So that's why here we should consider the characteristic like this. Okay, now if you observe the second point, the magnitude mod of h of omega cannot be constant in any finite range of frequencies, and the transition from pass band to stop band cannot be infinitely sharp. So here this one is ideal low pass filter cannot agree this one. Okay, that's why here if you take this practical filter here, that the transition band characteristic is not the sharp. That means here it is slowly decreasing, right? There is no abrupt change from pass band to stop band like this, and then there is no unity gain. So here also there is no unity gain, constant. Okay, and then here this is called as pass band ripple, this is called as stop band ripple, and this is the transition band, that is the band between the pass band and the stop band. And here let it be del 1, 1 plus del 1 and 1 minus del 2, and here is a del 2. Del 1 is the pass band ripple value, del 2 is the stop band ripple value, omega p, omega s. Okay, now here, so you should, the specifications here we should consider to do the any filter design. Here those are mainly 4 specifications are required. The first one is the maximum tolerable pass band ripple, so del 1 or del p, the maximum tolerable stop band ripple, del 2 or del s, the pass band edge frequency omega p, the stop band edge frequency omega s. Based on these specifications, we can select the system parameters like AK, BK. So this is the filter for a example for the practical low pass filter. To design this type of filter, we need the specifications del 1, del 2, omega p, omega s. Based on this only we can design the filter, that is low pass filter. Okay, now coming to the design of FIR filters. Okay, now here to design the FIR filters we have the different steps, and now firstly to do that we need frequency response of linear phase FIR filters. So here firstly we start with this here based on the n value, that means it may be either odd or even, and based on the type of the filter impulse response sequence, either symmetric or antisymmetric, we have 4 possible types of linear phase FIR filters. The case one is symmetrical impulse response when n is odd, symmetrical impulse response when n is even, antisymmetrical impulse response when n is odd, antisymmetrical impulse response when n is even. So here dear students, you should know about the frequency response of these 4 cases. That means frequency response of the filter is denoted as h of omega. So you should develop the expression for the expression, that is h of omega for the each case. Okay, so that will be discussed in the next one. Okay, now to do that, here firstly for these 2 what is that? Symmetric and anti-symmetric nature of the h of n. And for n odd and for n even, we have the 4 cases. These are just an examples. Discrete sequence, that is the impulse response h of n for n is odd. In the symmetric case means here, this is the h of n. So I am taking here almost 7 impulses. So from 0 to 6 means 7 impulses. Here n is odd. So 0 to 6. And here, what is the center of symmetry here? This is the 1. That means 0, 1, 2, 3. 3 is the center of symmetry. So here, from this, we can easily say that if you decompose this one, how can you decompose this one? From 0 to 2 is one part, 3 is alone, and remaining part is 4 to 6, like that. And you can decompose this into the 3 parts. One is the 0 to here less than n minus 1 by 2. Okay, and then this is the n minus 1 by 2, and next one beyond the n minus 1 by 2 to n minus 1, that is the another part. Okay, remember this decomposition of the n index. Okay, so this is about the center of symmetry, and it is also called as alpha. Alpha is here n minus 1 by 2. Okay, here n minus 1 is 6, 6 by 2 is the 3. Okay, you can check like that one also. And coming to the n is even here, this is an example. Here I am taking n is 8. Now 0 to 7 impulses are there, and then here the center of symmetry is this one. Center of symmetry means here from this, that means this is the demarcation line, and that and above that line and below of that line, the impulses magnitudes are equal. Okay, so now this is the center of symmetry. Now if you observe here, so magnitudes are equal here. Okay, from this and from this, and that means 0 magnitude is equal to 7 magnitude. Okay, like that, even symmetry like that. Now here, how can you decompose here the n index here? This is nothing but 0 to n minus 1 means here n minus 1 by 2 is nothing but here 3.5. This is the value. That means below of that line, 0 to less than n minus 1 by 2 and is one part, and greater than n minus 1 by 2 to n minus 1 is the another part. Okay, for n is even, we can decompose this n index into 2 parts only. Okay, now coming to the anti-symmetric, and here this is just an example for that. If you consider this is the center of symmetry, now here the magnitudes are equal but opposite in sign. Here n is odd one, and of course if you observe the center value is alpha n minus 1 by 2, almost that magnitude is 0 here. That means h of n minus 1 by 2 is equal to 0 in this case. Okay, in this case, and then here we can separate the n index like here also 3. One is at n minus 1 by 2, another one is greater than n minus 1 by 2, another one is less than n minus 1 by 2. Coming to the anti-symmetry, here n is even. Here also, if you observe this one, so center of symmetry is here. We can split the n into 2 parts. One is less than n minus 1 by 2, another one is greater than n minus 1 by 2. And then here, of course, we know that for the symmetric, the h of n is, for the symmetric, the condition is h of n is equal to h of n minus 1 minus small n, and for this h of n should be equal to minus h of n minus 1 minus small n. Okay, that will be given here. See this symmetric conditions, very important. For symmetrical, h of n should be equal to h of capital N minus 1 minus small n, and for antisymmetrical, h of n is equal to minus of h of n minus 1 minus n. So now here we should develop the equations for all the 4 cases based on these conditions. Okay, frequency response equation h of omega. Okay, so now it is the time for doing the derivation. Okay.